The world outside the cockpit is a blur of blue and green. The fighter jet screams through the sky at over 500 miles per hour. Everything feels normal. The engine hums with immense power. The controls are steady. The pilot is focused on the mission ahead. Then, in a fraction of a second, the world changes. A dark shape appears directly in the flight path. There is no time to react, no time to even process the image. The impact is a violent, deafening bang, not a thud. It sounds like a bomb has gone off just inches from the pilot's head. The pilot's heart hammers against their ribs. The entire airframe shudders from the force of the collision. Was it the canopy? The engine? A sudden spiderweb-like crack might spread across the windshield, obscuring vision. A plume of smoke could trail from an engine, followed by a terrifying shudder and loss of thrust. This is the reality of a bird strike. It is not a minor inconvenience. It is a sudden, life-threatening emergency that can cripple a billion-dollar aircraft and endanger its pilot. The quiet hum of the jet is replaced by the shriek of alarms and the struggle to maintain control. These moments are not just theoretical possibilities discussed in a briefing room. They happen. Pilots have faced these exact scenarios, forced to make split-second decisions with damaged equipment and shattered nerves. The sheer kinetic energy involved is staggering. A 4-pound bird hitting a jet flying at 600 miles per hour strikes with the force of a small car dropped from a 3-story building. This is the brutal physics that engineers must contend with. They cannot prevent every bird from flying into a jet's path, but they can, and must, design the jet to survive the encounter. This is where the story of safety begins. It begins with understanding that violent, chaotic moment of impact. The goal of bird strike testing is to recreate that shock, that explosive force, in a controlled environment. It is about taking the worst-case scenario from the open sky and bringing it into the laboratory. Here, the raw danger can be measured, analyzed, and ultimately defeated. The work is methodical and deliberate, driven by the memory of every pilot who has faced that sudden, terrifying bang, and the determination to ensure future pilots come home safely. The immediate aftermath of a bird strike is pure chaos. For the engineers on the ground, however, chaos is not an option. Their job is to turn the pilot's frightening experience into cold, hard data. What exactly happens when bird meets machine at high speed? They must replicate the event with scientific precision. This is not about guessing, it's about simulating precise conditions. From the size of the bird to the speed of the aircraft, 2 primary vulnerability areas demand scrutiny. Engines. Airframe. Especially the cockpit canopy. Engine ingestion tests simulate a bird sucked into a running jet engine. Spinning fan blades are the first point of contact. Can the blades withstand the impact without shattering? If blades break, where do the fragments go? Goals. The engine keeps running or can be shut down safely without causing a catastrophic failure that destroys the aircraft. Structural tests focus on airframe and windshield notch canopy integrity. Concern. Pilot safety and the aircraft's skin and control surfaces. A canopy strike must not penetrate the cockpit. Penetration can be fatal from direct impact, or from explosive decompression and wind blast. A strike to a wing leading edge or tailfin must not compromise controllability. Engineers run highly structured experiments, not random throws. Tests follow strict protocols defining bird projectile weight, impact velocity, specific test location on the component, common test weights, 2 pounds, 4 pounds, 8 pounds, sometimes, species range, to large geese. Tests simulate the most challenging yet plausible scenarios a pilot might face. To simulate a high-speed bird strike, you need a way to accelerate a bird to the speed of a fighter jet. The primary tool for this job is a device known as a chicken gun or a bird strike cannon, a large-caliber compressed air cannon designed to launch bird carcasses with pinpoint accuracy at speeds exceeding 700 miles per hour. The cannon barrel is aimed at a specific point on the test article engine intake cockpit canopy on a rigid test stand. Ammunition prep matters. Most certified tests use real bird carcasses. Chickens, turkeys sourced from food processing plants. They meet weight requirements, e.g., a 4-pound bird for many critical tests. Carcasses are weighed, often frozen, to preserve structure. Standardization allows engineers to compare results. In R&D, substitutes are used. Gelatin projectiles, synthetic birds, bird slime calibrated for weight, density, impact. Substitutes offer consistency useful for preliminary tests. A jet engine is a finely balanced marvel of rotating machinery, operating under extreme temperatures and pressures. When a foreign object like a bird enters this environment, the results can be devastating. Engine ingestion testing is one of the most critical and visually dramatic safety checks. An entire engine is mounted on a heavily reinforced test stand. Fuel lines, electronic controls, instrumentation. The engine is spooled up to a specific power setting, maximum takeoff power, cruise power, to simulate real flight conditions. Once the engine is stable, the bird cannon fires. The carcass is aimed directly into the center of the engine intake. The first components to meet the bird are the massive fan blades at the front. These blades, often made of advanced titanium composite materials, are the engine's first line of defense. In slow-motion video, you can see the bird disintegrate as it hits the spinning blades. The blades themselves may bend, twist, or even break under the immense force. The key objective of the test is to see if the engine can contain the damage. Containment is a critical safety concept in engine design. If a fan blade breaks off, it becomes a high-velocity projectile inside the engine. A well-designed engine has a reinforced casing, often wrapped in materials like Kevlar, that is strong enough to stop these broken pieces from exiting the engine nacelle. If fragments were to escape, they could sever fuel lines, damage flight controls, or even penetrate the fuselage, leading to a catastrophic failure of the aircraft. The test verifies that this containment system works as designed. Following the impact, engineers assess the engine's condition. The test standards often do not require the engine to continue running at full power. Instead, they might specify that the engine must not catch fire, that it can be shut down safely by the pilot, and that no hazardous fragments have escaped the casing. Data from sensors inside the engine, measuring vibration, temperature, and pressure, tells the full story of the internal damage. This information is invaluable for designers. The canopy of a fighter jet is the pilot's window to the world, a bubble of transparency that must withstand incredible aerodynamic forces. It must also serve as a shield. A bird strike to the canopy is a direct threat to the pilot's life. The goal of canopy testing is to ensure that this transparent armor does not fail. For these tests, a complete forward fuselage section is mounted on a static rig including the canopy and the windshield. Inside the cockpit, a fully instrumented mannequin, or crash test dummy, is placed in the pilot's seat to measure the forces that might be transmitted through a flexing or partially failed canopy. The bird cannon is positioned to fire the carcass at the most vulnerable points. These locations are typically determined through computer simulations and analysis of real-world strike data. Common impact points include the direct center of the forward windshield and the curved area of the canopy directly above the pilot's head. The speed of the projectile is set to match the aircraft's operational speeds, often in the range of 400 to 600 knots, which is about 460 to 690 miles per hour. The moment of impact is, a brutal test of modern material science. Fighter canopies are not made of simple glass. They are sophisticated composite structures built from multiple layers of stretched acrylic polycarbonate bonded together with flexible inner layers. This laminated design is intended to absorb and distribute the energy of an impact. When the bird hits, the outer layer may shatter, but the flexible inner layers are designed to stretch and deform without breaking completely. The goal is to prevent penetration. Even a small piece of the bird or canopy entering the cockpit at that speed could be lethal. After the test, engineers meticulously examine the damage. They measure the depth and spread of any cracks. They check for delamination between the layers. They analyze the data from sensors on the dummy to see if the pilot would have been injured by the canopy flexing inward. The high-speed video is studied frame by frame to understand the failure mechanics. If the canopy fails the test, it is back to the drawing board for the material scientists and engineers who will adjust the thickness composition or layering of the materials until it can withstand the required impact force. The raw violence of a bird strike test lasts for less time than it takes to blink. To understand what truly happens in those crucial milliseconds, engineers rely on a suite of advanced data collection tools. These instruments are the silent digital witnesses that record every detail of the event for later analysis. Without this precise data, the test would be little more than a visually spectacular but scientifically hollow exercise. The information gathered forms the bedrock upon which safer aircraft are built. High-speed cameras are the most visible part of this data-gathering effort. Multiple cameras are positioned around the test article, each focused on a different area of interest. One camera might be zoomed in on the exact point of impact, while another captures the overall response of the entire structure. These cameras, synchronized to a single time code, create a complete three-dimensional view of the event. The resulting slow-motion footage allows engineers to trace the path of debris, measure the speed of crack propagation, observe the deformation of materials in exquisite detail. Beyond the visual data, a network of electronic sensors provides a quantitative look at the forces at play. Strain gauges, which are tiny foil-like sensors bonded to the surface of the structure, measure how much the material stretches or compresses during impact. Accelerometers measure the g-forces experienced by different parts of the component. In engine tests, vibration sensors speed pickups, pressure transducers track the health of the rotating machinery second by second. All of this data is streamed in real time to a secure control room. This flood of information is recorded by high-speed data acquisition systems, which can sample the output from hundreds of sensors millions of times per second. After the test, engineers and analysts spend weeks, sometimes months, poring over this data. They correlate the sensor readings with the high-speed video to build a complete and coherent story of the impact. This detailed analysis reveals the hidden weaknesses in a design. A specific bolt that experienced too much shear, a structural frame that buckled unexpectedly, allowing for targeted, effective improvements. The purpose of every bird strike test is to generate knowledge that leads to tangible improvements in aircraft design. The data collected from a test is not just filed away, it is actively used to make fighter jets stronger and more resilient. When a test reveals a vulnerability, engineers are tasked with finding a solution, testing, analyzing, redesigning. This continuous cycle has dramatically improved aviation safety over the decades. The lessons learned in the test cell are directly translated into the hardware that protects a pilot's life. For example, if an engine test shows that fan blades are too susceptible to breaking, designers might change the blade's material to a more robust titanium alloy. Designers might change the blade's material to a new generation composite. They might also alter the shape of the blade, making its leading edge thicker, changing its curvature to better deflect an impact. If blade containment is an issue, the engine casing might be reinforced with additional layers of high-strength materials like Kevlar or Zylon, creating a stronger shield to catch any liberated fragments. Similarly, if a canopy test results in penetration or excessive cracking, the design team will respond. They might increase the thickness of the polycarbonate layers or introduce a new, more flexible interlayer material that is better at absorbing energy. Sometimes, the solution is not in the canopy itself, but in the supporting structure. The frame holding the canopy might be stiffened or redesigned to provide better support during an impact. These changes are then validated in a subsequent test, ensuring the fix is effective before it is implemented on the production line. The influence of testing extends beyond just materials and structures. The results can lead to changes in operational procedures for pilots. For instance, analysis of strike data might show that damage is significantly less severe at lower altitudes and at lower speeds. This can lead to new rules of engagement or flight protocols, advising pilots to reduce speed when flying through areas with high bird activity, such as near coastlines or wildlife refuges. This combination of stronger hardware and smarter procedures creates multiple layers of defense against the bird strike threat. Testing is not an arbitrary process. It is governed by a strict set of rules and standards developed over decades of experience and research. These standards ensure that tests are repeatable, meaningful, consistent. For civil aviation, regulatory bodies like the Federal Aviation Administration, FAA, European Union Aviation Safety Agency, EASA, set the requirements. They specify that critical surfaces like windshields, engine inlets must withstand impact from a 4-pound bird without hazardous failure. The military has its own, often more stringent set of standards. The U.S. Department of Defense uses military specifications, commonly known as MIL-STD, to define the requirements for combat aircraft. These standards, such as MIL-STD 810, include detailed procedures for bird strike testing. They dictate bird weights, impact velocities, angles of impact, pass, fail criteria for each component. Because fighter jets often fly faster and at lower altitudes than commercial airliners, their testing requirements can be even more demanding. These standards provide a clear, objective benchmark for safety. When an aircraft component successfully passes a certified bird strike test, it means it has met a universally recognized level of resilience. This is not a guarantee that no bird strike will ever cause damage. but it provides a high degree of confidence that the aircraft can survive the most common and dangerous types of encounters. The standards force manufacturers to engineer for durability, rather than just performance and cost. Furthermore, these regulations evolve over time, as new data from in-service incidents becomes available, or as aircraft capabilities change, the standards are updated. For instance, as jets become faster, the required impact velocities in the tests may increase. As new, lightweight composite materials are introduced, new test methodologies may be needed to understand their unique failure modes. This constant refinement of the rules ensures that safety engineering keeps pace with the advancement of aviation technology. The story of bird strike testing is a powerful testament to the relentless pursuit of aviation safety. It is a field where a moment of violent impact is transformed into a lesson in engineering, and where those lessons build an unseen shield around every pilot who takes to the sky. The work is far from over. As aircraft technology advances, so too must the science of safety testing. The next generation of fighter jets, novel materials, unique airframe shapes, advanced propulsion systems, will present new challenges and require new solutions. The future of testing will see an even greater integration of physical and virtual methods. Computer simulations, using powerful finite element analysis software, are becoming increasingly sophisticated. These models allow engineers to run thousands of virtual bird strike tests, exploring different impact scenarios and design modifications, far more quickly and cheaply than physical testing allows. However, these simulations will always need to be anchored in reality. The data from physical cannon tests will remain the gold standard, used to validate and refine the accuracy of the computer models. New materials, advanced carbon fiber composites, self-healing polymers, offer the promise of lighter and stronger airframes, but their behavior under high-speed impact is not yet fully understood. Each new material will require a rigorous campaign of testing to characterize its resilience and ensure it provides the protection pilots need. Similarly, the advent of new propulsion systems, such as those being developed for hypersonic aircraft, will demand entirely new approaches to ingestion testing, as the physics of impact at Mach 5 are vastly different from those at subsonic speeds. Ultimately, the goal remains unchanged, to ensure that when a pilot climbs into the cockpit, their aircraft is as safe as humanly and technologically possible. Every successful flight is a quiet victory for the hundreds of engineers, technicians, and scientists who work behind the scenes. They are the ones who face the explosive power of a bird strike in the controlled confines of a test cell, so that pilots do not have to face its consequences in the unforgiving environment of the open sky. Their work continues, a constant and vital effort to turn the shock of impact into the science of survival.